Hello, this is Professor D, and I'm going to do a short lecture on the binomial model, section 6.3 of our textbook. First thing we need to know about the binomial model is there are a fixed number of trials, and only two outcomes are possible: yes or no, success or failure, heads or tails. The perfect example of a binomial model is flipping a fair coin, and you could say a success was a head, a failure was a tail. There are only two possible outcomes. The probability of success, P, is the same for each trial, and the trials are independent of each other. So let's look at a couple of scenarios. 40 randomly selected college students were asked if they selected their major in order to get a good job. So the question is this a yes or no, true or false type answer? And it is binomial because the answer is yes or no. Only two outcomes. Now, 35 randomly selected Americans were asked what country their mothers were born in. Well, are there going to be only two outcomes? No. They could say the U.S., Canada, Mexico, somewhere in Europe. There are multiple outcomes. Now, if you change this question and you said you asked 35 randomly selected Americans whether or not their mother was born in the United States, then the answer becomes yes or no, because there is only two possible outcomes. But the original example is not binomial. So to estimate the probability that students will pass an exam, the professor records a study group success on the exam. So again, do we have two outcomes? Do we have pass, fail, success, non-success? Yes, we have two outcomes. However, the outcomes are not independent. He's using the study group to model what he thinks the class will do. And one of the tenets of the binomial model is that they are independent. So independence is not evidence here. Okay, so a couple of things. Binomial models may be used if the respondents of a survey are selected with replacement. Okay, and if the selection is done without replacement, the population size has to be at least 10 times larger than the sample size. Then you can still use the binomial model as an approximation. This will make more sense as we move further in and do some examples. All right, so again, here is a binomial distribution. The probability of success is 0.2. The number of trials was fixed at 8. And this is what the outcome looked like. It didn't look too good. Now, we have a higher number of trials, 12. The probability of success is 0.4. Looks a little bit more like our normal distribution. Look at this. Look at the third example. The probability of success is 0.6. Getting close to 0.5. We have a large number of trials, and we're starting to approach what looks like a normal curve. So if our number of trials, our N, is large, and our probability of success is close, relatively close to 0.5, then you can, the binomial distribution is approximately normal. And that's important later. All right, so when we do these binomial problems, we actually will let the technology, and I'll show you that, we'll let the technology do the work for us, but you have to know how to use the technology. So exactly is an equal sign. Less than, a less than sign. At least, this is where we start to get confused. At least, it's going to be greater than or equal to. More than, what do you guys think? In your heads, scream it out the computer. That's right, a more than sign, greater than sign. At most, less than or equal to. Okay? Now, let's look at some examples here. Less than and at least are complements. Remember, the sum of all the probabilities in a distribution are equal to 1. So if it was easier for you to find the less than in a problem, you could find the less than answer in a problem and subtract that from 1 to get the at least response. And then again, more than and at most are complements because those two probabilities will add to 1. Now, lucky for you, StatCrunch does most of the thinking for you. So you simply need to understand what's going on here. Okay? You simply need to be able to understand that in order to successfully use StatCrunch. How do we find a binomial probability? All right. 12% of all U.S. women will eventually develop breast cancer. 30 women are randomly selected. What is the probability that exactly 4 of them will eventually develop breast cancer? So let's think about what we know. The probability of success of getting breast cancer is 0.12. Okay? Our N is 30. And we want to find exactly X. So I'm going to say we're going to try to find the probability that X is exactly 4. Okay. I think this is going to... Now, when we run our binomial probabilities, it's in this form. If I don't, NPX. So when we're talking about binomial probabilities, we will write them in the form of B, parentheses, N, your number of trials, P, your probability of success, and X, your what you're trying to find. This is for an exact. Let's see if I can erase this. Let's erase all that ink. Okay. So how do we do this in StatCrunch? Well, let's go on over to StatCrunch. I've got a lot of stuff up here. Sorry, I'm going through again. Oh, got StatCrunch right here. Stat, calculators, binomial. All right. Our N is 30. Our probability of success was 12% or 0.12, and we wanted to find exactly 4. Let me hit compute. Okay, and that's what the distribution looks like. But the probability that exactly 4 women will get breast cancer is 0.2046, so about 21%. Again, let's just review the steps to get there. Stat, calculators, binomial. We put our N, which was 30, our P, which is 0.12, and exactly equal to 4. And then we hit compute. How great is that? How easy does that make it for us? Okay. About 0.2. Let's do another one. 14% of all clothing bought online is returned. If an online retailer sells 35 items of clothing, what is the probability that at least 5 will be returned? At least is, remember back from that last slide, greater than or equal to. Okay, so our N is 35. Our probability of success in this case is returning, and we're going to find the probability that X is greater than or equal to 5. Okay, and in StatCrunch, I already have forgotten. 35.14 greater than or equal to 5. Probability that X is greater than or equal to Compute. So that probability is about 0.554. Let's see if, and I think we agree. Let's keep going. Fewer than 7. So fewer than 7 does not include 7. So the one thing that we need to remember about this binomial model is fewer than 7 would be and back in the old days. I'm going to tell you how it was in the old days. You'd have to find the probability that exactly 1 was returned, plus the probability that exactly 2 was returned, plus the probability that exactly 3 were returned, all the way up through 6. So here, our probability is going to be less than 7. Again, stack crunch is your best friend. Come back here, probability that less than 7 are going to be returned is 0.789. So let's go with 0.79, because I'm pretty sure. Okay, I don't know why my computer, I'm sure your screens are flickering like crazy right now. Now, fewer than 7. Now the question is, could I easily figure out what the probability that 7 or more, okay, or we could say at least 7 will be returned, okay? Well, the sum of all the probabilities are equal to 1. Fewer than 7 does not include 7. That's the probability of 1 through 6. 7 or more, or at least 7, is going to be that probability from 7 through 35. So here, it's a complement. So fewer than 7 will be returned is 0.79. At least 7 will be returned would be 1 minus 0.79, which would equal 0.21. Okay, and this, all I'm talking about is if we wanted to find at least 7, those are complements of each other. That's really the probability that x is greater than or equal to 7. And let's go ahead and erase that thing. Okay. More than 6. Again, probability that is greater than 6, because it doesn't include 6. And this is usually where you guys get lost. More than 6 is not 6 or more, it's just more than 6. So we would change our sign, more than 6, and we'd hit compute. And we end up with 0.21. Okay. At most 4. I think you guys are getting bored of this lecture already because I bet it's starting to make a lot of sense. At most 4 would really be the probability of 1 plus 2 plus 3 plus 4. So probability of what? X is less than or equal to 4. And again, we would just come back to stack crunch, and we would use less than or equal to 4 and hit compute. All right, changing gears. You can also find the expected value with binomial probabilities and the standard deviation. Okay. So if we have a 6-sided die, has numbers 1 through 6 on it, and we roll it 30 times, how many times would we expect to roll a 2? Well, we'd expect to roll a 2 1 out of 6 times. So that's the probability. 1 out of 6 is the probability of rolling that 2. In 30 trials, we would expect to take the number of trials, multiply it by the probability, and that's how many times we would expect to see a 2 roll. Okay? In our binomial distribution, mu, the mean, is equal to n times p. So that mean is called the expected value. What would we expect? We can also find the standard deviation. So a binomial distribution with n trials and a probability of success p has a standard deviation of, their sigma is equal to the square root of n times p times 1 minus p. And in this case, let's go with a different color, our sigma would equal the square root of our 30 trials times p, probability of success is 1 over 6 times 1 minus p, which would be 5 times 5 over 6. And we would multiply that out in our calculator. Okay. Let's do an example. On a particular day, there's a 6% chance of fatal accidents in the city. Find the mean and standard deviation for the number of accidents in a 365-day year. So our P is 0.06. Our number of trials is 365. To find the mean, we're going to multiply the 365 times its probability, which is 0.06, which equals 21.9. And then to find our standard deviation, we do the square root of P. Here's our P. Times, oh, I take that back. This is our N. That's not our P. 365 is our N. We're going to multiply that by our P. And then we're also going to multiply that by our 1 minus P. So our standard deviation is 4.5. So we would expect to have 21.9 fatal accidents in a year with a standard deviation of 4.5 approximately. And that, I think, all right, let's look at this case study and then we'll be done. McDonald's claims that its ice cream cones weigh about 3.18 ounces. However, one of the authors bought 5 cones and found that all 5 weighed more than that. The question is that result surprising? Okay, so let's assume ice cream weights are normally distributed or at least symmetric around the mean. All right. So N, we'll say our number of trials was 5, and the probability of it being correct, okay, is either it is correct or it's not correct. So our probability here is going to be 0.5. Either it's going to be the right weight or it's not going to be the right weight. So we find the probability that X equals 5, that all 5 cones have this weight issue, okay, is a little bit weird. So if the true mean is 3.18 ounces, as McDonald's claims, then there's only approximately a 3.1% chance that out of 5 randomly chosen cones, all of them will weigh above 3.18 ounces. So I think that the hard part here is that P. Either they weighed 3.18 ounces or they weighed above 3.18 ounces, okay? And that's where we came up with our P. So it gives us an idea of a real world situation. So probably so in that particular McDonald's, maybe it's a training issue. So maybe somebody comes in and says, you know, based on the number of ice cream cones you sold last month, you're using too much ice cream. They do things like that. This would be a little test for that. Okay. So again, StatCrunch is our best friend here. If we look at in Pearson, your NPX, I don't know if I can make this a little bit bigger. Make it bigger so it's easier for you to read. All right. Identifying, oopsies, NP and X. All right. in the 2008, let's look at A. In the 2008 presidential election, 54% of the voters voted for President Obama. What is the probability that 65 out of 100 independently chosen voters voted for President Obama? So let's do this with me. If we're going to try to write this in the form B parentheses N comma P comma X, it is binomial. Either you voted for President Obama or you didn't. Okay? Our N here is 100 trials. Our probability of success is 0.54, and our X value would be 65. So in using StatCrunch, stat calculators, binomial, and remember in the lecture for 6.2 we were using the normal calculator. N was 100, probability 0.54, and we wanted to find, what was it, exactly, I'm going to go with 65, I can't remember, 65, 64. Okay? That exactly 0.006. So it's an interesting result. Let's go back to that. Because you want to find the probability that exactly 65 out of 100 voters. So you would expect that to be a small probability because overall 54% of the voters. So what would happen if we change this to 0.54? I wonder what would happen here. What the probability would be. Oh, not 0.54, 54. That's my bad. That's really the expected value. Okay, 0.08. Let's look at one more example, and then I will let you guys go. Let's look at this. Student is taking a multiple choice test. Each question has 4 options, A, B, C, and D. One of these 4 options is correct, and 3 of them are incorrect. What is the probability that the student correctly answers exactly 6 out of the 10 questions on the test by guessing? So what's the probability that they get a question right? It's 0.25, okay? Because if they're just guessing, they could guess A, B, C, or D. So it's a 1 out of 4 chance. If they, so our P here is 0.25. Our N, the number of trials, is 10. And we want to know if they get exactly 6 of those questions right. So our trials were 10, probability of success 0.25, and we want to find if the probability of them guessing 6 right. Okay, about 0.01. What's the probability of them getting all the questions on the test right? It's going to be tiny. Yeah, there's almost no way you could get 100 on the test. This probability is less than 1%. All right. Well, thank you for listening. We are done. And let me know if you have any questions.